to my math teaching online again. Before I get into the next unit of our second calculus course, which is the unit 3, I think, about the unit 3 or 4, I don't remember. It will be about the area under the curve. But there are many things before we get right into the topic. So I just treat this video as like a warm-up exercise for you to prepare you to the next unit. Now in this warm-up exercise, because it's related to our topic, so I would like to review a little bit the basic concept in the past you have learned in Math 11, Math 12, and just consider this warm-up exercise. So you are free, you don't have to do a lot of practice in this unit, in this video. Just watching the video as your warm-up exercise. The main thing is about the area under the curve, which is the next unit. But this video is prepared for you to do that. So let me review for you the past lesson. If you still remember, in the past you have learned the sequence and series. So what is a sequence? Sequence is the repeating patterns of a numerical value. For example, let's say example 1, you have an arithmetic sequence. Let's say 5, 7, 9, 11, and continue, blah, 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 right? Now you can see we call this a sequence because each term here based on the previous term adding 2. So the previous term add 2 give you the next term. And because you add 2 to each term, this is the same pattern and you're repeating it. So we call a sequence. And each number here we call term 1, term 2, term 3, blah, blah, blah. So now you know what sequence means. Now, this one is arithmetic sequence. Now let me give you another example of geometric sequence. So let's say you have example 2. Let's say you have geometric sequence of 1 over 2, adding 1 over 4, 1 over 6, 1 over 8, 1 over 16, blah, blah, blah. Okay, and let's say it end up here. So again, you see this is the sequence, but we call it geometric sequence because each term is multiplied with 1 over 2 to get to the next term. So this 2 times with 2 to get to 4. And 4 here times with 2 to actually this look like 2 times 1, right? And this is 2 times 2, and 2 times 3, and 2 times 4, so on. Okay, so this is like a pattern of multiplication for the denominator. So that's why we call this is a geometric sequence. Okay, so now, what is a series? So the series is the same like a sequence, except that we adding these terms together. So we add term 1, add term 2, add term 3, add term 4, and finally we get to the sum of the series. Now the sum of series is the sum of the sequence actually, right? So we add them together and we call series. Sequence is just repeating pattern without adding them. The series is we add them together. We add each on the term together. Sometimes we have a convergent series and sometimes we have divergent. It means we keep adding it and it keep going, it keep growing without stop, right? So we call it convergent or divergent series. Now today you will learn another thing, notation and of the series, of the sum of the series, and that notation we call a sigma notation. So sigma notation is just another way of writing the series in the short form, right? And that is a mathematical notation. So let me show you how to write this. Let's say this is the series. You add them together, right? Let's say you add them. So instead of comma, you will add them. Add this term together, right? So when you add them, you're gonna write the sigma notation. So you will say, and look like a Z, but I don't know, but the E actually, right? The E reverse, right? Okay. So this is like a E letter, E reverse, stand for sigma notation. And on the top, you will see the N number here represent for the number term. So let's say the term N up here, how many terms we have? 1, 2, 3, 4, 5. So N here equals 5 terms. And underneath here, we represent the I, which is start from the level 1. So let's say I equals 1. Now, based on this series, we're going to write them in the way that we can find the pattern. So we're going to say this is a fraction, so I'm going to write 1 over 2i. And why do I write like that? The reason because if you have I equal 1, then you time 2 times 1 is just 2, so you get the first term. And you know that you're adding to the next term will be 2 times 2, we're going 1 over 4. And next term, 2 times 3, you're going 1 over 6, and so on, right? And we know that we only go up to 5 terms. So this is a sigma notation. So instead of writing the whole pattern like that, you just write it in sigma notation. So that is the short form for this adding the sum of the series. Okay, so now you understand all of this term, we get right into the exercise, okay? So let's say if you have an exercise number 1, is say, write X series in an expanded form. So for example, I give you this sigma notation and I ask you to write in this form, expanding them, right? So that's the exercise. So let's say you have to write let's say 5 and then I equal 1 and the pattern is I square at 1. Okay, so the first one look like that, which is a very easy and simple one, right? And I know you will know how to do that. But anyway, let me show you. So I equal 1, our first term will be 1 square at 1. Now we're going to add this with the second will be, we start from 1. Now the I here will be replaced by 2 square plus 1 plus 3 square plus 1 plus 4 square plus 1 plus 5 square plus 1. So this will give us 2, adding with 4 at 1 is 5, adding with 10, adding with 16 at 1, 17, adding with 25 at 1 is 26. And after we add them, we know that this will be equal 60. Okay. So that's how you do it. Now, let's do another one, look more serious. Let's say if you have a sigma notation, and this is 4, and I equal 1, and you have I divide by 4, and f of I. So how are we going to write this in expanded form? So the first will be 1 over 4. F of I is 1, right? F of 1. Adding with the second one will be 2 over 4, which is the same like 1 over 2, right? F of 2. Adding with the third one is third one will be, okay, so that is I over 4. So 1 over 4, 2 over 2. No, what I'm doing. So I over 4. Okay, so 1 over 4, and then 2 over 4 is 1/2, F2, and then 3 over 4, F of 3, adding with 4 over 4, which is just 1, F of 4. Right? Okay. And how many terms we should have? 1, 2, 3, 4 terms. So that will become, I think that's it. We're not going to summarize it. Okay. So now I'm going to give you another example. And each example getting a little bit harder, right? And as I told you, you don't have to do this very much. I just want to make this video to for you as a warm-up exercise. And if for some people haven't learned the sigma notation, at least now you get used to with it, right? So that's my purpose. So now I'm going to say the next one, let's say you have an n, and I equal 1 again. And now you have 3 over n, f of 1 plus 3 over 4, I. So get complicated more, right? Now, this is n, and it doesn't say how many terms we're supposed to have, right? Okay, so let's see how we're going to write this. So I'm going to say the first one is 3 and over 1, right? F of 1 at 3 over 4 times with I is 1, so just 1, right? The next one will be 3 over 2, F times with 1 plus, just follow the pattern, right? Times with 2. So that 1, this is 2, and 3 over 3, F times 1 plus 3 over 4 times with 3. Now this pattern keep going, right? Same pattern because it doesn't say how many terms we have. So we're not going to, write a lot of terms. Maybe give one more short. So 3 over 3, now 3 over 4, F times with 1 plus 3 over 4. I here is 4, right? And then adding with blah, blah, blah. So now we're going to say the next previous term will be 3 over n minus 1. Let's say the previous term before the last term, right? So last term is n, the previous term is 3 divided by n minus 1, f of 1 adding with 3 over 4. And the I here This I will represent by n minus 1 as well, right? Now, this is the previous term before the last term. So the last term will be 3 over n f of 1 adding with 3 over 4. And instead of n minus 1, this will be n. And that's it. So we just say, okay, we're going to keep going until the previous term, and then this the last term. Now, this looks a little bit ugly, so let's simplify a little bit. So this become 3 f. I'm going to do 4 denominator, the common denominator. So this is 7 over 4. Okay. Adding with 3 over 2 f. This is, okay, so I'm going to cancel this 2 with this 2 down here. So that become 2 and 3 is 5 over 2. Okay. Adding with 3 divided by 3 just 1. And then f times with 9 over 4. Okay, so this is 9 over 4. Adding 4, 9 add 4 is 30 over 4. So keep adding, blah, blah, blah. No, actually, we still have to do this. So 3 over 4, f. This will be, this 4 will cancel with this 4 down here. So we have 1 plus 3 is just 4. Now, this will keep going until we hit this. And I think for this number, we're not going to know what number we simplify. So just leave it like this, right? So 1 plus, yeah, just leave this for now. And 3 over 4 times with n minus 1. Adding with the last term, 3 over n f times with 1 plus 3 over 4 and times with n, right? So that's how it looks like. That's we simplify a little bit. That's it. So that is the 3 examples I show you. How to use the sigma notation, how we write in expanded form. Now our next exercise, okay, our next exercise go backward, right? So instead of write in expanded form, now we're to write it in sigma notation. So number 2, your exercise will be write a series in sigma notation. So now we're going to compact it, right? Notation. Okay, let's say the first example always easy. Let's say you have 1 and 4 and 7 and 10 and 13 and 16, blah, blah, blah. Okay, no, actually stop. Okay, so let's see how we're going to write this one. So now, instead of write like that, we'll say this will be equivalent to E reverse, sigma notation. And the n here is how many terms we have. 1, 2, 3. So 1 term, 2 term, 3, 4, 5, 6. So n here equals 6, right? We have 6 terms. 1, 2, 3, 4, 5, 6. Now the I will start equal 1. So look at this pattern. How we're going to make it become an algebraic expression to express this. So how we do that? Now if we start by, we say this is 1 at 3 is 4, 4 at 3 is 7. Yeah, we know that, right? 3 and add 3. But if we say 1 add 3, it's not going to give us 1, right? 1 add 3 will give us the second term, but what about the first term, right? So we cannot say this is I plus 3, even though we know the pattern is each of them add to the 3, right? So we're going to have to figure out a little bit now. Let's say, how do you get back to 1? Let's say if you say, let's say this like 3i minus 1 and see what it happened. So if I is 1, 3 times 1 is 3. 3 times 1 is not going to be 1. So how are we going to get to 1? If I equal 1, 3i, okay, what about 3i minus 2? So 3 times 1 is 3, 3 minus 2 is 1. Okay, so that, okay, it seems to be okay, right? Now let's go to the next one. If I equal 2, then 3 times 2 is 6, 6 minus 2 is 4. Oh, it's good. If I is 3, let's test now one more time. 3 times 3 is 9, 9 minus 2 is 7. So this expression seems to be okay. So that's how we write it in sigma notation. We compact it, right? So that's example A. Now let's see what example B look like. In color. Okay. So now I'm going to give you another example. And another example, let me see. Let's say you have something weird like this. 1 minus 1 plus 1 minus 1 plus 1 minus 1. And plus 1. Bunch of number 1 adding together, but they are different sides, right? The positive is negative, positive, negative, so they alternate between that. How do we going to write the sigma notation for this series? So let's try. So we're going to write E reverse, right? And how many terms we have? 1, 2, 3, 4, 5, 6, 7. So N here equals 7. We have 7 terms. I equal 1. Let's say start from 1. Now, because we have an alternative, right? So I'm not going to say 1, I'm going to say minus 1. And if we put I on top, what happens? If I equal 1, then this is not going to change. This will become negative 1, right? But the first term we have is not negative, but positive. So how do we get positive? So you remember any base to the power 0 will be equal 1. So I'm going to take away 1 here. So now if I equal 1, 1 minus 1 will give me 0, which is this negative will become positive. Now let's check. If I equal 2, then this will be 2 minus 1, and 2 minus 1 is 1. So minus 1 to the power 1 is just minus 1. So it seems to be okay, right? So that's how we write it in sigma notation. We test 2 terms and we get this. So that must be correct. Okay, so now let me give you another example. And it seems that I have to erase this stuff. Okay. So let's say if you have to write another expression, let's say C, let's say you have x plus x squared plus x to the power 3 plus x blah 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 to the x power n. So how are we going to write the sigma notation? So we'll write this, right? And we just say n here because we don't know how many terms that. And let's say I equal 1. So can we say this is x to the power I? I think so. Should be okay, right? So that's it. That's an easy one. Okay, let's say, let's give you another one here. Let's say if we have 1 over 6 and f 1 over 6 plus 2 over 6 and f 2 over 6 plus 3 over 6 and f 3 over 6. And blah, 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 right? So how are we going to write the sigma notation? So our sigma notation will be n again. We don't know how many terms we have. I will be equal 1 over 6, 2 over 6, 3 over 6. So I equal 1 again, right? And the expression should be 1 over 6. Or should be I over 6, right? Because we keep increasing the pattern. F of I over 6. So that's how it looks like, right? Okay, so we're done. Now, the next one will be express in terms of monomial summation. Summation. What do they mean, monomial summation? Okay, let me show you what monomial summation means. Okay, so what is monomial summation mean? Let's see the first example. So let's say the first one, you have n here, and I equal 1, and you have 2 plus I on of this square. Okay, so how we write it in monomial summation? Express terms of monomial summation. No, express terms of monomial summation. So this is the monomial summation. We're going to write the expression for this in sigma notation, right? So let's say, so let me expand this, right? So this bracket is just the same like 2a squared, which is 2 to the power 2 is 4, plus 2 times a times b, which is 4i, right? 2 times a times b. And the last term is b squared, I squared. So this expression, when we expand, this is how it looks like, right? So now we will write it in sigma notation. We will write like this. I equal 1 for, let's go back from here. So you will have I squared. Adding which, next term will be, now we can bring 4 as a constant outside, and inside we have I. Adding which, last term is 4 times with n. So that's how we express in we express the terms of monomial become like that. Okay, so now let's give you another example. Let's say you have 20 and I equal 1. And the expression is 3i squared minus 12i. Okay, so how we express this? So now I'm going to say you can bring the 3 outside, and inside we have like this, I plus 1, and that's I square, right? Minus, you can bring the 12 outside, because it's a constant, we can bring it outside. 20, I equal 1, and this is I. So that's how we express this in the term. Okay, so that's easy, right? Now give you a last example. Let's say if you have n here, I equal 1, and you have 2i to the power 3 minus 3i squared plus 5i minus 12. So how we express this? Which is easy. Just say n, I equal 1. So we bring 2 and I 3 minus 3 and I equal 1 and I square plus 5 and I equal 1 I and minus 12n. So that's how we do it. Okay. Now, this is how you get familiar with the sigma notation in this video. The next part of this video, we will talk about the sum of the natural numbers. So we will have the sum of the natural number. And you will see how exciting about the sum of natural numbers look like. So let me show you the sum of the natural number. Okay, and this is definitely related to our lesson in the next unit. So let's say we have the sum of natural number. And our first sum look like this. N, I 1, and I. Now, it turned out this will become n times n plus 1 on of this over 2. That is the first sum of natural number. We have the second one. So I just introduce you the first one, right? Now I'm going to introduce you the second one. The second one look like this. It's going to be fun. So n and I equal 1. And let's say I square. So this will become n times with n plus 1 times with 2n plus 1 all of this divided by 6. The third sum, so this is the sum, right, of the natural number. So this is I equal this expression and I square equal this expression. So now the third one will be I to the power 3, and this will be equal n squared times with n plus 1, all of them square, all of this over 4. Okay, so these are the sum of natural number. This we call the sum of the first natural number. This is we call the sum of the square of natural number. And this we call the sum of the cubic of natural number. We call the sum of cubes of the natural number, the sum of the square of natural number. Okay, now why do we learn all of this? You will see it's related to the area under the curve. However, let's keep the secret for now, right? I am introduce you this, but I have to prove it to you for you to believe that, oh, this equals this expression. I square the sum of the natural number of the square will be equal to this expression. And the sum of the natural number of the cube will be equal to this expression. I want to show you where do we get that. How do we get this formula? How do we perform this formula? So what the lesson we will learn today? In the last, we have seen, in the last lesson, we have seen the sigma notation. And we were talking about the sum of the natural number. And usually in any spatial algebra expression, mathematical expression, we always have a formula. And these formulas are proven, and therefore they are very useful as the tools for us to perform our integration, antiderivative, whatever it is. So why is the sigma notation? And remember, I have went through with you these three formulas. So I know that I have to spend a long talk today and a long proof of the algebra proofing to all of you today. I knew that I have to use the home board so that I have enough room. So therefore, I just want to remind you about these three big algebra expressions we have learned so far about the sigma notation. The first one is the sum of natural number. And the second one is the sum of the square of natural number. And the third one is the sum of the cube of the natural numbers. And you can see on the left is the sigma notation and equivalent to the expression to the right. So I'm going to prove it to you. These equations are valid. It means the left side equals the right hand side. So now let me walk you through the first one first. So for the first one, let's say if we have to add all the terms of the natural number. So I'm going to call this number 1, and I'm going to work through it. let's say if I have to add them, right? So let's say if I add number 1, add 2, add 3, add, of course, 4, and so on, right? Until I hit the next level, which is the one previous term before the last term, right? And if you have an n term, let's say you have 1, 2, 3, 4, 5, and the 5 is your last term, then the previous of them would be the 4. If you have a 16 is the last term, then the previous will be 15. And how do we get that? It means the last term minus 1, right? So that's why we put n minus 1. That is the term before the last term, right? So next, final will be the n term. So the n here represents for any term. Let's say if we have 16 terms, then the n here is 16. If we have 5 terms, the n equals 5. If we have 100 terms, the n is equal to 100. So the n minus 1 before would be 99, right? N minus 1. So let's get familiar with this expression. So all what I do is just adding this term together, 1 and 2 and 3, but because they are long, so we just represent by n minus 1 and n for the last term. And we can add up to 1,000, doesn't matter, whatever, right, the last term is. So we represent in general by n terms, and n minus 1 is the previous term before the last term. Now, let's say I call this is the sum 1. So I say S1, right? So S1 equals all of this, right? At the end, I will add to get the sum, which is the total of it, right? So I call it the S1. Let's say if I rearrange it, and actually this method is from the Gorge. His name is Gorge. I think he's a German mathematician who invented this this proof. So I'm going to rearrange it, right? So I'm going to say, now I'm going to do exactly the same, but except I will bring the last term to here. So I will have n, that's the last term, adding with n minus 1, that's the term, previous term before last term. And of course, it will be n minus 2, so on, right? N minus 3, blah, blah, blah. But we're not going to write it, and we'll leave it like this. So our final term, let's say it will be 3 at 2 at 1, right? We reverse. So we list the sum of it the same. However, we just list the final term first, and then we reverse the process, right? We reverse the list. So this is the beginning to the end. Now we put the end and then go down to the list to the beginning. So that's how we rearrange them. Now let's say if I add some 1 and some these two sum together, and I just call it S for now, okay? So now let's say if I add them, so I'm going to draw the line, and say I'm going to add them. Okay. So when I add them, what do I get? On the right hand side, I will have 2s, right, to sum. 1 at 1 is 2, 2s. Now let's add from the left side here. So from my left side here, what do I have? 1 plus n. So I'm going to put n first. N plus 1, adding. Now the second term adding with this 1. What happened? minus 1, 2 at minus 1 is just 1. So this will cancel with this, right? And I have n plus 1. Instead of n plus 2, but because we have minus 1 here, so become n plus 1. The next one, this will cancel with this. 3 minus 2 is 1, so I ended up with n plus 1 as well. And these patterns will be the same. So it keeps like this for each of them, right? So this will cancel with something, and this one will cancel with this one. So this will become n plus 1 as well. And this will also n plus 1, the last term, n plus 1, right? So now all of them turn out to be n plus 1, n plus 1, n plus 1. All of them, the same pattern, the same expression. Except what? Except that on the right-hand side, we have 2 sum instead of 1 sum, right? Our purpose is to add 1 time, but we do like this to get 2 times, right? So we accept the true, how many terms we have. Whatever n term we have, this is how many n plus 1 term we have. So this is the first term, second, 3, 4, 5, 6, 7, so on up to 100 if this n equal 100 terms. If this n is 50 terms, then all of this will be first term, 2 term, third term, 4 term, up to the last one is 50 terms. So we can summarize this expression as 2s plus, 2s on the right hand side equal, the number of terms is n, right? How many terms we have? If we have 50 terms, we substitute n by 50. If we have 100, we substitute n by 100. And we don't know how many terms we have. We just assume that we keep adding, right? Now it could be 4, 5, 6 terms, whatever we decided. So the n here is stand for the number of terms. How many terms we add them together. And time with n plus 1, right? We time with n plus 1. And because we have 2 sum, but we just want 1 sum. So at the end, we divide it by 2 to get 1 sum. And that will go here. So S will be equal to this. Now, if you look back, the first expression right here, is that exactly the same formula we got here? N times m plus 1 divided by 2. N times m plus 1 divided by 2. S equal. Now, instead of writing S, we can write it in terms of the sigma notation, like we learned in the lesson before. We say we have n term. Let's start by I equal 1. And the natural number stand by I. It's the same 1, but we don't want to say 1. We just say I. And we add each I together. So the first I is 1, the second I is 2, the third I is 3, 4, so on, right? So this is how this sigma notation represented. So now I have proven to you, yes, this is true. That expression is correct. Now, I am not proving this, actually. We learned it from the mathematician, the German mathematician, his name is Gauss. I think G-A-U-Z. Don't remember what is his last name. I should remember, actually, but I just remember his first name, okay? So he came up with this famous proof of the first sum of natural number. So that is the first proof I show you. Now I'm going to go to the second proof, which is I squared. Okay, so let me erase this so that we have room to do it. And so to you, the sum of the natural square is equal to this expression. So this proof will be a lot more difficult, but let's take a look. So let's say if I have a sum of the natural square, so I put s square, equal 1 square plus 2 square plus 3 square plus so on, 4 square and so on until we hit the previous term, n minus 1 square plus n square. So that is the sum. Now, let's see how we're going to do this. So I'm going to add 1 here. I'm going to power 3. And here I'm going to have 2. Next term will be 2 at 1 power 3. Next term will be 3 at 1 to power 3 and blah, blah, blah. So this pattern will go on and until we hit n plus 1 all of them power 3 equal. Okay. Now this is requiring us to get back to the formula of A plus B to the power 3 will be equal A to power 3 plus 3 times A square B to power 1 adding with 3 A to power 1 B square, and the last term will be B to power 3. So we have A and B, right? So we have A to power 3 for the first one, and the last one is B to power 3. Now this, I'm going to apply exactly to this bracket. So I'm going to have, first term will be 1 to power 3, right? Time with 3 times A square, which is 1 square, and time with, and adding with 3 times 1 to power 1 and times 1 to power square, and adding with last one will be 1 to power 3. Okay, so that is how it looked like. It's a little bit rounded. I don't like it. So maybe, sorry, I'm going to rewrite it to make it further apart so it's easy to look. So the first one is 1 to power 3. Adding with the second one is 3 times with 1 square times with 1 and adding with 3 times 1 and 1 square, and the last term is 1 to power 3. So we follow exactly the formula here. You see that, right? So now the second one will be the same, except this term will be 2. Everything else is just exactly the same formula, right? And this will be 2 square times with 1. Adding, go to this bar, 3 times 2 times 1 square. We put them like this. 1 square. Okay, so 3 times A times B square. Yeah, so plus 1 to power 3. Now the next one we'll do the same, right? So it will be 3 to power 3. Add 3 times with, instead of 2, it will be 3, but exactly formula the same. So this pattern is just rewrite it, right? So that is 3 times with 1 square, adding with 1 to power 3. Now, the next one will be n to power 3, adding with 3 times with n to power square times 1, adding with 3 times n times with 1 square adding with 1 to power 3. And this keep going, right? So that's how we apply the formula and we expand the binomial bracket. Okay, so let me iterate this formula and we're going to add them together to see what happens. So now I'm going to add them. We'll draw the line here, and here, and I'm going to add them. See how it happens. Okay, so on the left, I'm going to copy this down, n plus 1 to power 3 equal. Now remember these are the sums, so we add them together, right? We add them together. But what happened? This is the left-hand side of the equation. This is the right-hand side, right? Remember, if you have a number, if you have, let's say if you have a number like this, right? Equal sign. If you bring this number, okay, so this is like 8 equal 8, right? What happens if they are the same? And if you move this to the other equation, so a minus a equals 0, it cancels out, right? So instead of doing like this, I just say I'm going to cancel if they look the same on the left-hand side and on the right-hand side. If they 8 and a and just cancel it, equals 0, right? So that's the scenario. So now, let's see what I can cancel them. So if you look at here, we have 1 and 1 is 2 to power 3. On the left, we have 2 to power 3 on the right. If I move this number to here, I can cancel them and they gone, right? So it's just the same line I just read to you. Now I have 2 at 1 is 3, 3 to power 3, 3 to power 3. The same, cancel. And this pattern will continue going on, right? Until the one before this and this one as well. Okay? Now let's look at the rest. If I add all of this, the one I circle, now look at the one I circle. I have 1 square, add 2 square, add 3 square, add n square, just like this one pattern, right? Now let's look at the second pattern. What do I have? When I circle, I have 1, add 2, add 3, add blah, 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 right? Add that, we add blah, 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 keep going. So let me write down in summary. After I cancel this, what do I get? So I get this one, which is 1 to power 3, adding. This is the factor 3. I can put in factor 3, right? They on 3, 3, 3, time with. This is just the same line as square. This is 1 square, add 2 square, add 3 square, blah, blah, the last term n square. So I'm just write this 3 times with s square. Makes sense, right? And time with 1 doesn't matter, it's the same, right? Adding, this is 3 as well. What is it? 1 plus 2 plus 3 plus blah, 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 n. So this is the first sum. So 3s, right? Sum 1. And the last term is 1 to power 3. But how many terms of 1 to power 3 I add together? 1 add 2 add 3, n term, right? Go up to here is n term. So this 1 times to power 3 times n as well. And 1 to power 3 is just n, just 1, and 1 times n is just n, right? So I can leave it like that or can cancel that and just put n, doesn't matter, right? So everybody see this. Now I'm going to substitute. This, I still leave it the same way. For this one, I'm going to just put 1 instead of 1 power 3, they are the same. Adding with 3. Now, instead of s squared, actually, I still can put s squared for now, okay? Because that's what I want to solve for, right? I want to solve for you to see that s squared. Adding with blah, 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 blah. This will be 3. But instead of s, I'm going to substitute by the first root we already know. This is the sum of natural number of the first one, right? When we add 1, add 2, add 3, add 4, so on. So I'm going to write in terms of n. In the right-hand side, I'm using this because we already proved it, right? From Gauss method. Gauss method. So we learned that from Gauss method, and we know how to do it. This, so I substitute the sum of the first natural number into here, okay? So that's how it looks like. The last one, I'm going to get it 1 power 3, just write n, okay? Same thing. So now, I have to prove to you that finally I will get all the way from here to this expression, right? To this one. Okay. Now, let's see what we can do. So I'm going to move this to the left. So I say 3s squared will be equal. I'm going to move this to the right. Okay. No, actually, I keep them separate. Sorry. But, so this is right side, this is left side. I just bring it to the left, but I keep this on the right. So they're not changing anything, right? Everything here just stay the same. N plus 1, I just rearrange them, but actually 3s squared equal n plus 1 power 3, 3s squared equal n plus 1 power 3. I'm not changing anything, right? I just change the position without twisting the sign because they're separate, left and right, right? So they just stay like that. Except I try this one first, okay? And then I try this. It makes no difference, okay? However, let's see. Now, if I continue with these terms, so this already take care, right? This I already move out over there. And this already take care, I move here back, but it doesn't change. However, these terms have to be changed aside if I separate them from this guy, right? So it's like I toss it to the left, actually. So it will be positive will become negative when I do that, right? And this will be the 3 over 2, right? So that will be 3 over 2. So I move this and I change this, like I subtract this term. So 3 over 2 n times n plus 1. Okay, minus this as well, n plus 1, right? I just combine this n plus 1 here. Become n plus 1 minus that. Okay, so this equal this, subtract all of this stuff left over, right? So that makes sense. Now, I want to factor out, so I'm going to say this is 3s squared equal. I would just say they have n plus 1, they have n plus 1 in here, n plus 1. So I factor out the common factor, which is I call it n plus 1 in all of them. I factor out, and therefore, I'm going to, after I factor out this, I need to multiply back to get exactly the same, this expression. So the first one will be n plus 1 power square, because power square with power 1 give me power 3, right? Give me this one. Now the next one will be minus 3 over 2. And this will be n plus 1 I already have here, right? So I'm going to say minus 3 over 2n because this already here, have it here. Minus n plus 1 already here, so just 1. Okay, so I have to simplify this. So I'm going to say this will be equal, therefore, 3s squared will be equal now, because I want to solve for s squared, let's just solve it, okay? So I divide this by 3, and I cancel that, right? Left, right, when bring to the right, it multiply, become divide. So now I'm going to write n plus 1 over 3 time with, I want to expand this bracket, right? Because I know this formula. This is just a plus b perfect formula, which is equal n squared plus 2n plus 1 square, which is just 1, minus 3 over 2 and minus 1. Okay, so now I'm going to have to bring it up to here because I don't have room. So we have s squared equal n plus 1 over 3. And you know what? Let me put down here so that you see it. N plus 1 over 3, right? Time with, I want to summarize this one, right? I'm going to make uncommon denominator the same, like 2 to 2, so we can add them, right? So that will become 2n squared, 4 plus 4n plus 2 minus 3n minus 2. And all of this will be over the same common denominator, right? So I just do common denominator, so that 2n squared plus 4n plus 2 minus 2, 3n minus 2 over all of them over 2. Okay, so I'm going to cancel whatever I can do in here. Plus 2 minus 2 gone, right? 4n minus 3n. So 4n minus 3n equal 1n. So I left with n plus 1. I'm going to tie these two guys together. 3 times 2 is 6. And here, I draw it at 2n squared at 4n minus 3n is 1n. So now factor one more time. N plus 1 over 6 time with n squared time with, actually just n, time with 2n plus 1. So now let's look at the root I prove it. This is equal s squared. Are they the same? Exactly look the same. N times n plus 1 bracket time with bracket 2n plus 1 over 6. So now I have proved to you that this is true, right? So the sum of the natural number square equal this expression. It's exactly true, okay? So this is the second proof. Now the last proof, I have to go through with you for this proof. So I have to erase the bar, and sorry about that. So everybody see what I'm doing very obviously, right? Finally, this equal, after I go through all of this work, right? Okay, natural of the cube number. Okay, so the sum of the natural cubes number, I wrote it here. So when we add 1 to the power 3, add 2 to the power 3, add 3 to the power 3, blah, blah, blah. And add to the previous term n minus 1 to the power 3, and the last term n to the power 3 equals s to the power 3. So how do we get from the long way to this expression down here? Let's see. Now, before I show you the proof of this, I have to show you a little bit related materials you learned in the past. I think that some of you know about the Pascal Triangle. And the Pascal Triangle in about 165. So he's famous for this well-known triangle pattern, right? So let's say if you have, an A plus B, you know what? Sorry about that. I'm going to write it in the place that is not interfere with us. So let's say if you have a plus b to the power 0, then it equals 1. A plus b to the power 1, it will be equal 1, 1. A plus b to the power 2 equal 1, 1 add 1, 2, and then 1. A plus b to the power 3 equal 1, 1 add 2 is 3, 2 add 1 is 3, and 1. So now if we have a plus b to the power 4 will be equal 1, and 1 add 3 is 4, 3 add 3 is 6, and 3 add 1 is 4, and 1. So they call it Pascal triangle because it looks like a triangle, right? Shape, right? And this is the pattern when you do a binomial to the power, okay? So what we look at now is look at the last expression here. Everything on the top, we don't have to worry. Now, I just show you, we did the a plus b to the power 3 before, but we use another formula, right? But you also can use this formula as well, okay? So let me erase the thing on me. So now we just focus to that one, and you will see. We use this coefficient, right? So let's say if I have 1 plus 1 to the power 4, and the second one will be 2 plus 1 to the power 4, and the third one is 3 plus 1 to the power 4, and blah, 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 continue up to n plus 1 to the power 4, equal. So, I need more room. Okay. So this is on the left side. On the right side, we'll follow this pattern. This is a plus b to the power 4. This is my a, this is my b. I follow that. The first one will be 1 to the power 4. Adding with 4, that coefficient. These are just the number of coefficients in front of the terms, right? The term you have to know from going down from the power, right? So 4 times with, first one will be 1. See 1 to the power 4, so now 1 to the power 3 times with 1 to the power 0. So it's just 1. Now we will adding with, I'm going to put here 6. So it's 6. So 4 and then 6, right? 6, 1. This is 1 power 3, 1 power square. This is 1 power square. Adding with 4 times. So that 1 will it go down from 4 to 3 to 2, and now it's to 1, and this will gain to 3, and the last term will be 1 to the power 4. Okay, so we follow just the coefficient here. You see that, see 1, and then this is 4, and this is A and B we call, right? So now follow that, this will become 4 times with 2 to the power 3 times 1 plus 6 times with 1 square times 1 square plus 4 times, and actually this should be 2. 2, yeah, and 1 to the power 3 plus 1 to the power 4. This will be 1 to the power 4 plus 4 times A is 3, right? This number, power 3 times 1 plus 6 times 3 power square times 1 plus 4 times 3 times 1 power 3 plus 1 power 4. So this pattern, we just keep going like that, right? Keep going. And the last will be n to the power of 4, adding with 4 times n to the power 3, adding with 1, adding with 6, times n, times n to the power 3, times 1, adding with 4, times n, times 1 to the power 3, adding with 1 to the power 4, right? So that's how we expand it. Now, when we add them, what do we get? Let's cancel before we add. Oh, my mistake, sorry, my bad. Should be 2 and this should be 3. So 1 at 1 to the power 4 is this number. 1 at 1, 2 to the power 4. Cancel, cancel. 2 at 1 is 3 to the power 4, 3 to the power 4. Cancel the left, cancel the right, right? 3 plus 1 to the power 4, of course, it will be cancelled. And the term before this one will be cancelled with the term down here, right? So now, what we left over? We left over with this. This is 1 plus 1 to the power 4, adding with this will be, I'm going to circle this for you to see, right? Circle that, and I'm going to circle this. And this should be square, sorry. And I'm going to circle this as well. Okay, so now what it look like? This is 4, and this is the sum of the cube. 1 to the power 3 like this, adding with 2 to the power 3, adding 3 to the power 3, blah, blah, so on. So I can call this as S of cube to power cube, power 3, right? I substitute this. Now, adding with 6, all of this is the sum of the second square, the power square, the natural. So I'm calling this S power 2, and this adding with 4 and with the sum of natural number, right? Just S, which is this one. This one is S, this one is equal to S square, and this one is equal to S power 3, okay? So now I am going to substitute. Let's see how do I substitute it. So this is stay the same. Instead of 1 to the power 4, just say 1, okay? Adding with 4. I'm going to time this with, because we already proved, no, we not proved this yet. So I still keep it as like this. Adding with 6. We'll substitute S square by this expression, because this is how we already prove it, right? So we know this is true, so I'm going to substitute S squared equal this. So I'm going to substitute this in, and that is n times n plus 1 times with 2n plus 1. All of this divided by 6, right? Adding with 4, and the s is the sum of the first term here, right? So that would be times with n plus 1 divided by 2. Adding with last term, the last term here is 1 to the power 4. 1 to the power 4, but times with how many terms? N term, right? So n times 1 to the power 4. And actually, I should put it here. And I'm going to erase this, just time with n for now. Okay? So now I'm going to write it in a decent way. 6 divided by 6 is 1, gone. 4 divided by 2 is 2. So I'm going to say, and I'm going to bring this over, right? 4s3, I'm going to bring it over. 4s power 3 equal. I'm going to say equal this, right? N plus 1 is still on the separate side, so I don't bother to change the side, right? However, when I write this stuff, I say this, subtract this, right? So I have to twist the side for this one here. Now, for this one, I just leave it for now. I'm going to do, and this, we already tossed over here, right? So I'm going to do this here. And this gone, it's become 1. So it's just n times n plus 1 times with 2n plus 1. Adding with 4 divided by 2, it's become 2 times with n times n plus 1. Adding with the last term, I will add this to this, right? N plus 1. Okay? So now, what do? I will say solve for S3. So S3 will be equal this one here, n plus 1. And I'm going to factor out, right? I'm going to factor out this because I have n plus 1 here, I have n plus 1 here, and this is, what is it? It's n times n plus 1 times 2n plus 1, that's right. So I have n plus 1 here and I have n plus 1 here. So all of them have a common factor of n plus 1, right? So that's why I'm going to factor out the n plus 1. I'm going to open the big bracket. This will become n plus 1 to power 3 because when I tie back, I get back to power 4 here, right? So that's for this one. And now the next one, I have this already. So I only have to tie it with this one and this bracket. And the next one, I have this already out here. So I will have to tie with 2n. And the last one will be minus, because everything become minus, right? So be careful, that should be minus as well. And this should be minus. And this one I already have here, so it should be 1. Okay? So that's how I factor out and I summarize this, become this. Are you following me? I hope so. Okay. So now, what do I do next? I am going to divide this by 4 and I'm going to cancel this here, right? So S3 will be equal to n plus 1 over 4 times with, I'm going to simplify this, I'm going to expand this one, right? So that becomes n to the power 3 plus 3n squared plus 3n n plus 1. So that's the first term. And the second term will be n times 2n will become 2n squared minus n. And minus 2n minus 1. So now I'm going to simplify this again. We have n plus 1 over 4 times with, okay, let's see what happened. 3n squared minus 2n squared. This become n to the power 3 plus 1n squared, right? This minus that is n squared. 3n minus 1n minus 2n, so that cancel with both of this, right? And I left with 1 minus 1, so that gone also, and just this. So now I'm going to put summarize s to the power 3 will be equal n plus 1 over 4. And I'm going to factor out this, right? Times with n times n squared times with n plus 1. Okay, so now let's see what happened. I'm going to put it here, go up here, right? I will have s to the power 3 equal, I have two of this, so I'm going to combine this guy and this guy. So I make n plus 1 square, because I have two of them, right? To the power 2 times with n squared. All of this divided by 4. So yes, I have proved this formula correct. You see, the sum of the cube root equals n plus 1 squared times n squared divided by 4. This is how I get the same exactly. Okay, so it's a long proof today lesson. And you know what? You don't have to do with the proof, except that as the instructor, we try to show to you, convince you that these formulas are correct, so that you accept it. You more easily to accept it when you see it the next time, because you will not question where this come from, why it like that, right? But now you know, if we add on this 1 plus 2 plus 3, you can use this formula. And depend on how many terms you add them, right? And depend on the number they give it to you. You can just toss it in and use that. If you add on the square together, 1 square and 2 square and 3 square, you know you can use this formula because you know it's true. So that's why the purpose is, as the instructor, we want to show you this proof. Now, I'm not be able to show you every single proof, right? Because I'm not genius. Maybe there's a ton of them out there. I don't know how to prove it. And I haven't learned how to prove it. These basic stuff, I already learned and I show you, right? Now, why do I show you this proof? Because the next lesson in the next unit in our calculus 2, we will learn the area under the curve and this summation related to that. And so that's why I toss it in as food for thought, like not necessarily have to be in the calculus 2, but it's good if you know it, right? And I taught this in our course because I told you I designed the course in very depth level and detail. So I want to show you, to share with you the knowledge I learned. I have it, I earned it in the past, and I want to show to you. And also, you will see some professor might go through with you this, maybe not, maybe the other one, but in general, math have universal language. So whatever you learn, you will see it Not right now, maybe in the future, whatever. Okay, so I hope you enjoyed this long proof video. So I'm going to end the lesson right now, and stay tuned for our next lesson. And I hope you enjoyed this long proof. And now you know about sigma notation, and how the sum of natural came from, and what are their formula. So you will see maybe they are useful. So thank you for watching, and bye for now. Merry Christmas to all of you.